is Walter Jairo. Last time we gave you an assignment on the area that was covered on electrochemistry, which was on writing a unique equation, write the cell representation, and then calculating the EMF of the cell. We are going to start by looking at the first problem on a unique equation. That is a summary of the overall reaction taking place in the cell. And the electrons given are already on the wall. Silver reacting with magnesium. The first thing that you look at is the sign of electrode potential. And you can see that silver has a positive electrode potential and magnesium has a negative electrode potential. Now from this you can easily predict which electrode is undergoing oxidation and which one is undergoing reduction. Now the one with a positive electrode potential will undergo oxidation. It's the oxidizing agent, and the one with a negative electrode potential is the reducing agent. So in this case, silver is the oxidizing agent and magnesium is the reducing agent. Now in an electrochemical cell, the oxidizing agent always undergoes oxidation and the reducing agent, oxidizing agent undergoes reduction and reducing agent undergoes oxidation in the chemical reaction in the cell. So in this particular case, silver is the oxidizing agent, so it will be reduced, and then magnesium, which is the reducing agent, will be oxidized. So the first thing is to identify the species that is undergoing oxidation and the species that is undergoing reduction for you to be able to write a unique equation. So silver, having a positive electrode potential, is the oxidizing agent, so in the reaction it undergoes reduction. And what is reduced is the ion in the electrolyte, that is silver. So silver, you write the half reaction for the reaction taking place in the silver half cell, where silver is being reduced, changing it to silver solid. And then you write the corresponding electrode potential beside it. But that may not be necessary at the moment, because that will only be helpful when you are now calculating the EMF of the cell. So for a unique equation, we can ignore the electrode potential and simply write the species, the half reactions taking place. Therefore, in magnesium, being a reducing agent, it will always undergo oxidation, which means loss of electron. So magnesium solid will lose electron, forming magnesium ion plus electron. And therefore, if you add the two half equations, then you end up getting the overall ionic equation for the reaction taking place in the cell. So in this particular case, therefore, you simply add the spaces on the right hand side and the spaces on the left hand side to get your ionic equation. So we will have magnesium solid, silver. We are through with the left hand side. Then the right hand side, we write the spaces on. So this one now will represent the ionic equation taking place in the cell, and that will be our answer for part A. Now when you go to part B, you write the cell representation. The cell representation is also the same as cell notation. So how is cell representation written, or cell notation, or writing a cell diagram? So this always comes from the ionic equation. Which species is undergoing oxidation and which species is undergoing reduction. Therefore, we pick it from the ionic equation. And so magnesium will be changing from magnesium solid to magnesium ion, and then silver will be changing from silver ion to silver solid. And therefore, when writing a cell notation, conventionally, the oxidation reaction is always written on the left-hand side, and the reduction reaction is always written on the right-hand side. So that we start by writing the half cell where oxidation occurs, then the last one will be the half cell where reduction occurs. And the two half cells are separated by electrode, by salt bridge, which we represent by double arrow. So oxidation will occur in magnesium half cell, and what reaction will occur is magnesium solid changing to magnesium ion, and then you separate it by an interface giving us magnesium ion solid, and then the two cells, half cells, are separated by a salt bridge which you write between, and then we end by writing the half cell where reduction occurs. So silver ion is changing to silver solid, and then conventionally it is always important for you also to indicate the overall cell potential for cell notation. So therefore it can also be useful for you simply to write the cell, the electrode potential, standard electrode potential for each cell, so that you also get you also obtain the cell electrode potential. So that this one now will be 0.80 volts positive, but this one, being that the way the cell is written, is normally written as a reduction, but on this other side is the reverse of what is represented in this equation. So when we reverse the equation, the sign of the standard electrode potential also reverses, so that we have, now being this one was negative, now it becomes positive value. So if you add this, like we are done in our earlier discussion, you get the overall cell potential, which is 7, this is 1, and this is 3. And obviously, as you can see, it has a positive value. So always in cell notation, it is just important for you also to include the overall cell potential, which is positive 3.17 volts. Then lastly, calculate the EMF of the cell, which already we have done in the process. Obviously, in our last discussion, we said you can use two formulas. You can write the half cells and then add them. And this one is even more useful because you will get this ionic equation plus the overall cell potential. But you can also use the formula of E reduced. E cell is equal to E reduced minus E oxidized. So this one can also be used to get the same value. Now the one that is reduced is magnesium, and the one that is reduced is silver. So it is positive 0.8 minus 2.37. The one that is oxidized, that is magnesium half cell, and then you get the same value that we have already obtained here, plus 3.17 volts. So you can use the two methods. The first one that we discussed earlier, and then this other last one where you now use this formula of E cell is equal to E reduced minus E oxidized, and then you get your value. So that is what you are expected to have obtained in our last lesson, where we gave you the assignment. So let me hope that all of you have gotten the right answers from here. In addition to what we have covered, you also need to know how to draw an electrochemical cell, where the oxidation reaction cell is written on the left-hand side, and the reduction or reaction cell is written on the right-hand side, and you also indicate the salt bridge plus the voltmeter. Then you also need to identify the anode and the cathode. The anode is where oxidation occurs, and cathode is where reduction occurs. So the anode in this case is magnesium, and the cathode in this case is silver. Then you also give the direction of electron flow. Electron will always flow from where oxidation occurs to where reduction occurs, and you indicate it on the diagram by indicating E with an arrow like that. So those three are very important information that you also need to know.